All right. I mean, this is part of your existence. So, what was the first project that somebody actually paid you some money to do something? What was your first sort of hardware project where you actually got paid to do it?
Well, so in high school, it was when there was cable descrambler boxes. It was before digital cable, and I had a teacher at my high school who got one of these boards and needed somebody to assemble it. And the electronics club screwed it up. Uh, they took a half-hearted attempt and like had it all messed up. So that summer, I convinced them to give me the board, and that if I got it to work, I forget it was like it's probably $20 or something, which and I spent about a month in this little crawl space, with my multimeter and my soldering iron, and got it to work. Delivered the board, got my $20, spent it all at the Pinball Arcade probably that same day. You know, so I mean, this is these were like, wow, people will actually pay you to do stuff with technology. That to me was like, I'd be doing this for free. I mean, I would pay to do this, but I have no money. I'm a kid growing up in Chicago. So I mean, I would gladly pay if I could, if I had money. But wait, you're going to pay me to do this? Like, oh yeah, I mean, I'll definitely do it.
And so you grew up, you grew up your childhood, I guess, at least in Chicago. That's interesting. I mean, Chicago was a much different place then than it is today. What else were you doing in Chicago when you're like in high school? Are you active in anything else, or you're just really focused on this sort of stuff?
Well, I think I was always the smartest of the bad kids, which was, a real problem for the teachers and administrators. Had a lot of calls back to my parents. That was like I stopped going to class a lot. Well, I just went to the computer lab all day, and nobody stopped me. You know, so that was a bit of a problem. I was also in a lot of bands. Music was my other great passion. It still is. I still love music. Um, so I was, kind of a, difficult kid. I think for
What year did you graduate high school?
1983.
Oh, 83. Oh, wow. So I'm curious then, I'm assuming you had the grades, but you were bored probably with all that other stuff. So did you decide to go to university? I don't know what it was. I mean, I graduated in 87. I know in 87 the expectation for everybody was to go to college at that point. And I probably didn't have the grades. I went to a state university in New York, but I went, right? I mean, that was the thing you did next. What was it in 83? Is it the same thing? Is you're just expected to go to university or?
Well, yes, of course. I was a year younger than everyone else just because I skipped first grade because I knew how to read already, which was quite tricky actually growing up, being a year younger than everybody. So I could not get into the university I wanted to at the time, which was UC Berkeley. Uh, so I ended up going to the University of California, San Diego, because they had a supercomputer there. They had a Cray. And I basically wanted to get my hands on that since what I really wanted to do was artificial intelligence, actually.
In
So my major,
1983.
yeah, so my major was a double major in computer science and cognitive psychology because there was no such thing as a field of study of AI. AI was like a research thing, maybe, like, out of the psych department or maybe the math department or.
Dude, how does that even come up on your radar screen in 1983?
Oh, no, this stuff well, it was because of a language called Lisp. So Lisp is a programming language that I believe it was invented in the late 60s, actually.
I had to do like 3 weeks of Lisp in university, and it was not fun.
Ah, it didn't, you know, many people say Lisp is like the LSD of programming languages. Like once you take it, like you're permanently altered by it. Like apparently you were immune to it, right? But a lot of us,
Recursion in parentheses. I don't know, dude. I don't think I was mature enough yet.
Yeah, this is possible. This is possible. These are very far out concepts. Um, but I was fortunate enough to get turned on to Lisp through some of my mentors that I had. Um, and looking at Lisp, it just, I knew, and the things that they were trying to do with it. I mean, a lot of things that we call AI is like, it's just anything we don't know how to do with programmers yet. Like things that we do now, like optical character recognition, right? That was AI back then. Like, oh wait, a machine that could actually read like writing, like wow, that's like AI, or chess, or chess playing, anything that you could do that seemed really difficult at the time was in this category of AI. Now it's just like, oh no, it's just OCR. It's just document processing at scale as we get all the claims forms. Like, what do you mean that's AI? That's not AI. That's just claims processing. So um, so I was lucky to get turned on to some of these ideas, and also because so when I was a teen, my parents had divorced. My mother lived in California, my father in Chicago. So because of my interests, um, and just because of my troublemaking personality as a child, I was shuttled back and forth between my parents at different points. So when I was in California, I was very lucky that the town where my mother lived was a town where Steve DeWitt and Alan Kay, who I think a lot of people know his name. So Steve is not as well known, but one of Alan's colleagues and one of my mentors. So I don't know if he took pity on me or just got sick of me or what. So they had opened up this retail establishment. I think it was called the Apple Tree. And the Apple Tree, the idea was for them, their big idea was we're going to open up a chain of retail establishments across the country, all filled with Apple II computers, and kids are going to come in and their parents are going to pay by the hour for them to use the computers. So this was all perfect for me except for the pay by the hour part. Like I had no money, right? And like I mean, I was another place I was thrown out of. But I mean, eventually they were like, I don't like I said, I'm not sure if they were sick of me or took pity on me, or maybe I did something interesting. I'm not sure what it was because I was really interested in pirating software and evading copy protection at the time on games. Right. I mean, whatever it was that caught their interest, um, Steve took me under his wing, and so I was one of these really fortunate people to receive the benefit of the wisdom and teachings of Steve and Alan and other people that came through there and just playing with computers and playing with ideas. So naturally,
Free compute time too, then.
yeah. Well, I think like richer kids' parents were paying so that I could be there. Or, I don't know. I mean,
Oh, you better watch out. Steve might send you a bill now, dude. Be careful.
but I mean, so I had some early exposure to some of these ideas. So by that point, like I already knew these were the things I wanted to work on, and um, but I didn't really have a chance to do anything of any significance until a couple years later. So I dropped out of the university to go work at Apple Computer because, well, obviously there was the Alan and Steve connection to Apple, but I was just really bored at university. It's just I, I wanted to do these things, and I had to take all these general ed classes and do all this stuff that wasn't. I didn't have the discipline, and I was doing apparently some kind of interesting things in computing enough to get this opportunity to get a job at Apple, which I just jumped at, right? I just jumped at.
Wait. So what was the job in, even if it's indirectly sort of offered to you, like, hey Ron, I think you should go apply over here, or did you just do that on your own initiative?
So there was this thing that had just come out called HyperCard. Now, HyperCard was sort of like the web before the web. It was a very innovative hypertext media programming system. Like if the web had not been on the internet, if it had been just a series of files on the disk, and if JavaScript had been a very friendly, human-like language, even more than it is for some people. And if every web page had a way that you could modify that page and create a new page from it, that was sort of like what HyperCard was. It was a way that individual users could create their own information, which they called stacks, and it was incredibly effective at getting domain experts, just people who knew subject matters, to be able to create their own information sources that people could then click on things and would go to another section and show you could play videos and audio and show pictures and write scripts that had logic in them and different things. For me, this was really, really exciting because I was really interested in hypertext and hypermedia because one of the other characters I ran into in my youth was somebody named Ted Nelson. This was back in Chicago. So Ted Nelson is known as the father of hypertext. He wrote a book called Dream Machines Computer Lib. Computer lib, man. People's, women's lib. I think it's like, it's a 70s book. So it's a double-sided book, like kind of like the Whole Earth catalog was, I think. You could turn it over and it'd be another book. So it was two books in one. And it was full of like drawings and collages and different fonts. And so Ted Nelson was a really innovative researcher. He had a project called Project Xanadu, which never really took off, but it was a lot of the ideas that are in the web today actually came out of this research that they did in, I think, it came out of some research they actually did during the World War II. There was a man named Vannevar Bush, who was the head of the science research for President Franklin Delano Roosevelt, because gathering information, collecting it, and getting it to the right people was a big part of how the Allies won the war. So he was trying to come up with a concept of how he would build a universal information retrieval system. Because remember, this is before computing. Like any computers there were machines that were designed to do complicated mathematical calculations and produce a singular result. This idea of interacting with a machine was really like science fiction. So Ted Nelson took those ideas and started trying to build them into things and published some books about this. And he actually opened one of the first computer retail stores in Evanston, Illinois, not too far from the campus of Northwestern University, which was one of the first universities to have a timeshare computing system called Plato. Timeshare computing was you could use a video tube terminal and a keyboard and get access to a computer that was someplace else for some fraction of time. Maybe it was an hour per day. That was your time to use that computer for something. So Ted Nelson opens the first computer store, selling the first microcomputers. I think he had things like that Altair in there, called the Itty Bitty Machine Company, like IBM, which naturally, eventually IBM sued him and made him change the name, but I think he already was going out of business because, a retail computer store in those days was like, a what? Nobody knew what that meant. But I rode my bicycle. I think I was in 7th grade or something. I had a Schwinn bike, like a BMX type bike, So I had an analog computer. So an analog computer is a different kind of computing that uses analog voltages instead of digital on and off signals in order to do the same type of mathematical operations. And this particular thing had, one of my father's friends gave it to me. It was like some 1950 salvage or something. It had these giant relays on it and tubes, and you programmed it using patch cables that you would plug in. Like the canonical program that you wrote was to solve the logic problem of you need to cross a river. You have a goat, a dog, and some corn, right? The goat will be eaten by the dog. The corn will be eaten by the goat. The boat only holds two of you. You have to figure out how to get everybody across the river. And so it would tell, kind of like Towers of Hanoi. It's like one of these classic computer, logic solution. So I took this analog computer, which looked like you would imagine a salvage analog computer with patch cables, taped it to the handlebars of my bike, and I rode down to this new computer store that I'd heard about from my friend, the Itty Bitty Machine Company. And I go in there and I untape it from my bike, so it's got like tape residue on it. And I go in there, and Ted Nelson's working the store. I have no idea who Ted Nelson is or anything. I don't know. I'm in seventh grade, and I'm just trying. I know this place has computers because I'm trying to see if they'll take a trade in of my analog computer to get one of these microcomputers.
Oh, that's funny.
So Ted Nelson looks at me like up and down, kind of, long haired, you know, just rode in on his bicycle with this thing. Says no, says no first, says no again, then says, but you could put notice on my bulletin board, which was an actual bulletin board, like like cork. You
Oh,
put
okay.
things in it.
Yeah, yeah,
So I
yeah,
wrote
yeah.
on the 3i5 index card, for sale, analog computer, you know, whatever. I think these digital computers were like $2,000, so I put on there like I don't know 500 or best offer. No calls, naturally. No hope, of course. And then he told me I could leave after I played with one of these computers for a while, and to take my analog computer with me because I wanted to leave it on consignment, but he wasn't having it. So I knew later I discovered who the guy was because I got gifted this book, which, by the way, that book, that copy of Computer Lib's Dream Machine is now in the hands of Steve Klobnik, who
Oh,
is an amazing software developer um, who is deeply involved in the Rust community these days. So he was really into hypermedia for a few years, and so I had to give that book to him because I thought he needed it more than I did.
yeah, nice.
But so I knew, I had some exposure to these ideas of what was artificial intelligence. I had some exposure to these ideas of what is hypertext and hypermedia. This was percolating in my young brain. So, um, so I came up with an idea, which was, as it turned out, the first expert system shell written in HyperCard. So what does that even mean? It means it was a system that was designed to use rules to represent knowledge about a particular domain and then apply those rules so that somebody could use one of these HyperCard stacks, which would run on any Mac, to then access the knowledge. And I thought this was really interesting because a rule-based system, would be like if the patient has a headache and the patient has not had water in the last 8 hours, then they may be dehydrated. And a series of these if-then rules applied in sort of a non-consecutive fashion, right? So that it's not like first one rule and then the other, but based on the listing of the rules in some text editor. These expert systems would look at all of the different rules and try to figure out which ones would apply in order to try to take some fact or information that you would tell it, like, the patient has a 103-degree fever, and then use that through a series of questions and interrogatories to try to come up with a diagnosis. One of the first expert systems was actually one specifically for doing this called MySyn, which I think was created like in the late 60s or early 70s, probably in Lisp. So I thought, all these ideas really sound the same to me. It's just like two sides of the same coin. So I made this thing HyperX, which was both a system for building expert systems and also an education system that taught you about the ideas behind them. So they thought that was pretty cool. And next thing I know, I'm, doing work at Apple, on things related to HyperCard.
Nice.
So it was a real big eye opening too, because I was, really young, really naive, you know.
How long did you stay there? How long were you at Apple?
So I think it was about 3 years, give or take. Um, things sort of it was a difficult time for Apple. It was during the five-color days. You know, eventually, like a lot of my strongest memories are when Jean-Louis Gasset was leading Apple, who then later went on to create something called the B operating system, BE, which is another one of these, way before its time, way too innovative. No, and that was really the case with Steve Jobs himself. Like a lot of the ideas that he was trying to embody into a piece of software and a piece of hardware and a product, they were just too far ahead of their time. And we look at them now. If you looked at the Newton, which was the Apple PDA, whatever it was, late '80s, you're like, oh, this thing's a joke. And then you look at the iPhone and you're like, aha, yeah, you were actually onto something. You were just, way too ahead of your time. So I mean, there's something to be said for being. You have to have the right timing. You know, Everybody thinks that they're too late, but you're probably too early.
My first company, I would say that we were putting, before Google Maps, uh, even before Zillow, we were putting houses on maps in browsers. We bought the Esri systems to generate the maps, right? JavaScript, pure Java, like we were, that was ahead of its time. And I built a UI that was powerful, but nobody could use it. It was, again, today it would be easy to use, right? And I learned a lesson there. I learned that um, I really, the lesson was I never had enough money to change, to be able to educate people enough under these new UIs and new sort of, right? Like Apple now has enough money to do that, right? They changed all the haptics all of a sudden. They have enough money to sort of do that. I didn't have enough money to teach people how to do those things. So I feel that like, damn, if I didn't know.
But even if you had the timing of it, like if it was too soon, then it would have been like, wow, cool thing, but I'm fine with my razor phone, right? Like there were a bunch of companies that passed on these ideas that could have did it. They could have been Apple, that, and there was a combination of different things that came together so that it was the problem people had at the right time with the right solution. So I mean, it's not that you didn't. I mean, maybe you didn't have enough. Maybe if you had enough time to keep at it long enough, you could have educated and brought the market on with you. That's also possible. Just because my crystal ball tends to be like the magic 8 ball. You shake it, it says answer unclear. Try again later, and then like try again later, and it says the same thing.
So what was your next thing? What gets you to leave Apple?
I actually started my own company um, at the time, Millennium Software, because this HyperX thing, that this was during the first AI bubble. Uh, so when people say AI winter, I'm like, yeah, I'm kind of familiar with that idea. So um, HyperX, we sold software. It was source included, but it was not open source. And we sold software to, wow, every university, every major university. I mean, like every major university. It was from on every continent. We sold software to the U.S. Department of the Navy. We sold, software to, Arthur Anderson and all the, consultancies. Just because everyone was really interested in what you could do, and but then the AI winter came and it just wiped out all of the companies in this sector. Were just like gone.
What year is this? Is this late 80s?
This is like 1989, 19 through like maybe 91 or something. You know, it's it's way way early. It's very similar to today in the sense that the early promise of some demos leads a bunch of businessy people to think that we're closer to a solution to their business problem than we actually are. They throw a bunch of money in, turns out not to be true. They're disillusioned, and they're like, the whole thing was fake. And it made me think. This was the first time I learned. I don't know if you've ever heard of Roy Amara. So Roy Amara was one of the people at the Palo Sapos Institute for the Future, which was a really innovative technology, think tank and experimentation center in the early days of Silicon Valley. So Roy Amara is the guy who said we have a tendency to overestimate the short-term effects of technology and underestimate the long-term effects of technology. right? We overestimate the short term and we underestimate the long term. And so they thought, similar to what a lot of companies who are pumping a lot of money into, machine learning, that, oh, we're really close to solving this problem if we just throw a bit more money in, and then we're going to be able to do for, a dime what currently costs $100, and as a result, we're going to, make a great deal of money, right? That's been, efficiency has been the goal with technology since the beginning, right? How can we be more efficient, whether it's with resources, with time, whatever the thing is, the purpose of technology to a large extent has always been about efficiency, right? We need to be able to mine things more efficiently. So what generates the steam engine, right? We need to be able to calculate these numbers more efficiently. So things like UNIVAC and ENIAC are developed. You know, we need to be able to make things that are really, really small. So photolithic technology, and lasers. And so, all of these things were about seeking a greater efficiency in some area. Information technology originally was part of the accounting department. There was no IT, right? It was part of accounting, and it was largely handling things like payroll, accounts payable, accounts receivable. This idea, like, yeah, we could use information devices for other things. They're like, I don't even know what that means if you tell them this in 1960. They're like, we go to the file cabinet, you know, but what if the file's not here? Oh, well, then we get on the phone and we call that office, and they send it in a courier, or if it's on the third floor, they send it in a pneumatic tube, or something like that, right? So this idea of like instant access to things is always about efficiency of information to, you know, improve the human condition in some way, right? Depending on how we do it.
But at that time you're making some money, and then the whole thing just sort of stops, is what you're saying, in the early 90s.
A lot of these things are, when you're looking at studying finance, which I've been, depending on how you look at it, either fortunate or unfortunate to have worked for a whole bunch of different financial companies in different sectors, in banking, in mortgage banking and commercial banking, actually, in mutual funds, not the same company, series of different companies, as I was slumming around, trying to figure out how to make a living um, over a number of years. But, you know, the thing that, all of these companies are really just trying to maximize the amount of revenues that they can produce. But you think it's very logical, right? You think it's very orderly. Like there's a system, like markets go up and down based on some type of logic, right? And there's a whole bunch of different, theories behind these different analysis. Well, there's another school called behavioral finance. And behavioral finance says markets have psychology and it's based on that, not on any actual facts, but only on the way that the market feels about the thing. And this explains a lot, because if you do fundamentals analysis, you're looking at things like, okay, how much money does the company have? How much do they make? What's their inventory? Are they owed a bunch of money that they're having trouble collecting, or are they sitting on piles of cash? Like, do they have research and development with like a new product about to come out next year that's going to change everything, or they're like they haven't come out with a new product in 3 years? Right? You look at this stuff and you think, okay, I should be able to figure out. Oh, no, sorry, wrong. Logical mind says this. Actual markets do things that make no sense. And so there's a school of research about behavioral finance. And it certainly explains companies where you wonder, how is this company worth so much in terms of their public valuation when they don't have as many companies that are customers, and they don't have as many products, and they don't have as many people working there, and yet they're worth the same as this long-standing company in the industry that basically dominates the whole industry. What your explanation for that? You'll come up with a bunch of really good ones, but actually, no, it's just how the market feels about it. So a lot of the pendular swings that occur, in terms of technology investing are often based on things that are not due to anything with the technology itself.
You know, I experienced this with people at Intel. I did a bunch of training at Intel, and there were groups that were building software projects that would never last more than 3 years, would never see the light of day. And I sat down one time and I asked somebody, like, this is the fourth project you're on at Intel. Intel makes all their money. Well, I don't know this, but they make let's say the bulk of their money is made on their processors, right? They're not making any money on these side software projects. Why do they keep doing it? And the person told me that the market feels like if Intel isn't innovating, that they're not worth investing in. That, yeah, there's a processor market there and it's making all the money and it's there, but what else are they doing? So they invest all this time and money in, I'm almost called them now, almost virtual projects just to make the market feel like they're innovating beyond just the hardware. It was mind blowing to me.
Well, it's just funny you mentioned Intel, and just because I have a bit of a history with Intel, about 5 years working with Intel, actually. Um, and innovation, it's, to me, it's kind of a dirty word, like, oh, innovation, because I can afford, I am lucky that I can say that only because I'm one of the recipients of Intel's Top Software Innovator Award um, 5 years in a row. So, so I could be a snob about, oh, these innovators don't know anything. I'm one of them. Look at me. I'm a perfect example. I know nothing. I'll give those things to anybody. Um, but I mean, so Intel did make money off of software. Um, actually, but it was not enough relative to the rest of the company. And it's really similar to the early days of Xbox and Microsoft. Like Xbox, dominant force in the video game industry. But at the time, Microsoft's money is all coming from licenses of Windows for the desktop. So it's like, oh, you kids are number one in video games. That's so cute. Let us know when you hit this many billions in revenue, though, because we're selling corporate licenses. Like, but that's so neat. And like, they were number one. Doesn't matter. Okay, they're making all this money. It doesn't matter because in the grand scheme of the company, it's just like a rounding error. If it was a separate company, if Intel's software and systems group had been a separate company, then it might have been better. On the one hand, on the other, it is true that no, you don't just simply deliver a chip and here it is. Good luck. That's not, any piece of hardware is actually all of the software that not just the software it uses internally, but all of the software that you use in order to make it work for you to solve the problems, the SDKs, the examples, the reference platform applications, the integrations with other pieces of hardware. There's, doing that when you are, if you only sell the chips and nothing to do with the software, right? This was a little bit how IBM, lost the narrative to Microsoft during the era when Microsoft managed to be providing an operating system that they then could sell to all of the arch competitors of IBM who was selling the hardware, right? The story of MS-DOS. So you do need to have software when you create hardware in order to create a complete package that some company could use to build a solution with. You cannot, outsource that completely or say, yeah, third parties will take care of it. On the other hand, you can't have vanity projects that are just around for the sake. Maybe some, right? Like you need some sizzle to the steak, if you know those phrases. When you are selling something, usually people buy the way it appears, not the substance. Like everyone wants to think they're rational. Like, yeah, I went to research. It was the best. You know, washing machine I could have possibly bought. But a lot of it has to do with, well, no, actually, it wasn't the one with the best specs. It was the one that looked the nicest. And aesthetics are not to be disregarded, right? There is a utility to the function of an aesthetic. The design is figuring out a thing that works. Otherwise, it's just art, right? Like a glass hammer could be very beautiful, but it breaks up to a million pieces when you use it, so it's not a good design, even if it might be a nice art piece, right? The design of a hammer has to do with the way you hold it and the way you strike with it. So, I mean, all of our things that we build have to have a utility, but also it needs to look nice. Like, there's a lot of companies that sell, I have HexClad cookware, and they're really attractive, and they work quite well, but they're very attractive. So this is an aspect of, the utility function is one, but also the aesthetic of how you feel about using it is another. So Intel's, they are having some difficult times. They had some really bad announcements recently um, about the profitability of the Intel Foundry, which is their attempt to function as a chip manufacturer, a contract manufacturer for other companies, a bit like the Taiwan semiconductor manufacturing company, one of the most important and interesting companies on earth, actually. Um, so Intel trying to do this is not a bad idea. It's just very late in the game, to be doing, and you know, I don't think it's violating any non-disclosures. They flew a group of us who were from different parts of the world to Chandler, Arizona once to speak at an executive briefing for a bunch of important Intel bigwigs. Um, I used to know a bunch of important people there. I was in Brian Kazanich, who was the CEO of Intel. I was in his keynote video one time as that guy. I was that guy for the Intel CEO one time. That's it. My claim to fame. I was that guy once. But they flew a bunch of us in, and these were very intelligent people coming from different markets and parts of the world and perspectives. And we had a whole panel discussion, and we were quizzed by hundreds of executives, and at the end, nothing happened. So, you know, it's a very complicated thing to run a company at galactic scale, and I'll let you know when I get it mastered myself.
I saw CNN did a report on that. They did a report on Taiwan and why it was so important, and with China and the whole thing. And they talked about this company that you just mentioned that manufactures all the chips and how important that company is to the entire planet, right? And I was thinking, like, why haven't we already started at some capacity, even if the federal government was going to fund it, to build some of that manufacturing here, just in case or when China takes over Taiwan, right? And that all ends, like to have this sort of backup at some capacity. Like it would make sense for Intel and AMD, I guess, right? To to have that capacity. I know how much more expensive it would be here, but this to me would be something that the government could subsidize. They would be worth subsidizing. No?
Well, this is happening. Um, so some of the things that have come out of the probably poorly named Inflation Reduction Act, um, and some of the other federal legislation. In fact, fairly recently, it was a very big purse of money to go to Intel, again, for this exact purpose. And um, there's a number of factors in play. One of them is the ability for the design of new processors, and then another separately is the manufacturing of them, right? So on the design side, there's a really interesting movement around something called RISC-V, or RISC-V, RISC-V. So RISC-V is an open source platform for actually building chips, for actually designing chips. So, historically, when we want what if we need a new chip? What would we do? Well, we'd go to Intel and they would say, oh, that's neat. Maybe someday we'll make a chip like that. Like, oh. Then we go to ARM and they'd say, oh, yeah, you can totally make a chip like that. First, give us a bunch of money. We'll give you the ARM reference designs, and then you can go off and make your chip. Like, wow, we don't have that kind of money. oh, she's, what do we do? You know, so RISC-V is an open source set of reference designs that if you want to start a chip manufacturer, you can just use these designs, put them together, and start manufacturing your own silicon based on, and these are things like arithmetic logic or floating point operations or just the very fundamental building blocks of computing. So RISC-V is really exciting because it now makes it possible to first have a standardization of chip design. And on the other hand, start with a standardization and then you want to make a chip that's really efficient at a particular type of machine learning processing. You can start with this RISC-V design and then add your secret sauce silicon things to it. So it's bad for incumbents in many ways because it disintermediates their so-called intellectual properties, some of which are kind of getting a little long in the tooth. But on the other, it's great to start a sort of Cambrian explosion of new hardware possibilities to do more things cheaply and more things more efficiently, or more things more powerfully, different axes. And just in case you think all is bad for Intel, one of the first investors in a company called Sci5, which is a company that is doing RISC-V technology, one of their first major investors was Intel Capital. So, there is some movement. It's just these things take a long time, and the needle to move on a market as big as computing, between desktops, small form factor PCs, IoT devices, servers of different kinds, uh, switches, and networking equipment. I mean, it takes a long time to make a big dent in the size of this market. So something that, again, going back to the short-term overestimation and long-term underestimation, it's easy to write off a big player like Intel, but, they are building factories and Chandler and other places, they are doing things. So it's, time will tell whether or not, they're able to achieve a transition from, highly proprietary to a much more adaptable, quicker to move, and it's, doing that with a battleship or an oil tanker, you don't drive it around like a speed boat.
Well, if they get into manufacturing, then having these basically modules of circuitry don't hurt them anymore, right? They just shift. They still have their proprietary chips, obviously, but at least it softens the blow because those people are coming to them anyway to manufacture it. So go at it, actually. Go have some fun.
And they had some the announcements actually about Intel specifically. One of the problems that they've had is they chose to use a slightly older technology. So the way chips are actually made is pretty amazing. If you've ever seen, they actually use lithography. They project a negative impression at a microscopic size upon this material, which causes it to change. And so then you look at it, and now the surface of this material is doped, as they say, so the electricity flows some ways and not other ways. And then because of the way that these semiconductors are aligned, they take the form of switches, and they do the same thing that valves did when they were vacuum tubes, actually. In fact, calling it a valve makes it very helpful to understand what a transistor does. Right? It's just, you turn on the valve and then the water flows through. And what if we have two valves? Well, we turn on this one, we turn off that one that comes out here, and if we turn off this one and on that one that comes out there. Like, oh yeah, I get it. That's why we're code plumbers, Bill. We're just code plumbers at the end of the day. It's all just plumbing, all the way down.
Instead of water, electricity.
But yeah, RISC-V is a very exciting new. I mean, it's not that new, but it's coming on quickly, and it's very good for creating a more distributed system for the manufacturing of the semiconductors and chips that we need to run our civilization. But one of the reasons why Intel ran into some problems was because they used a slightly older technology for the optical part instead of buying a newer technology actually from a company in the Netherlands, ADSL, which is really the innovators. In fact, one of their main customers is the Taiwan semiconductor manufacturing company. So, the supply chains are quite interconnected. The ability to make these machines is quite concentrated. I mean, you have to order a machine from ADSL, a few years in advance, and they ship it to you in like 40 shipping containers. I think, you know, this is the kind of scale of machinery that I've been working with the last few years, although not in semiconductor manufacturing, in battery manufacturing, actually.
Oh yeah. Well, we can have an entire show on batteries. So let's not even start going down that way. All right. Uh, We've been talking for almost 2 hours, but there's a little bit more I want to at least talk to you while I have you here. And I do want to talk about some TinyGo stuff with you.
Yeah, you gotta let me pimp out some
And
of my current projects.
yeah. I want to talk about TinyGo with you, and I'm kind of interested in why you could have done anything with TinyGo, right? You went down the seat, what is that? The computer vision route. Why computer vision? I understand why TinyGo,
Well,
I
those
want
are
you to
actually
talk
two
a little
different
bit.
projects. Those are actually
Oh, they are.
so. I know
I thought
it's.
you were doing CV. Okay,
I am also
go
doing that. I'm
talk
also
about
doing
it.
that.
I thought they were connected. So correct me. Talk about TinyGo and your CV stuff.
So sure. So TinyGo is a Go compiler written in Go, which can produce executables in places that Go is not able to normally execute. Because, for example, microcontrollers. Like a lot of people have seen, my badges. Like here's one of here's here's one of
Yeah,
here's
if you're watching the YouTube video, Ron is holding up one of his cool Gopher badges.
this is kind of bright. It's hard to a little hard to read. Actually, I need to inverse the screen. Let's see if I can flip it
Yeah,
up.
no,
Well,
I could see it pretty good. Oh, you're gonna turn it on.
yeah, no, you can actually see it doing something.
So Ron's got these things that look like gophers. They're probably about 5 inches long, and he puts a computer screen in the middle of it, and you can have your name or anything you want as a badge. It's
This
pretty
badge
cool.
is actually made by my good friend, collaborator, and TinyGo team member, Daniel Esteban, known as Conejo Ninja, and he's really the TinyGo crew toy maker. No, I'm like the toy maker emeritus. Uh, but uh, but yeah, he makes these badges. They run Go on them on the Raspberry Pi RP2040 chip, which is not like the Raspberry Pi single board Linux computer. No, this is an actual microcontroller. So just to kind of define what is a microcontroller, it's a chip that generally has a single core for processing that is at most 32-bit, sometimes 8-bit processors. Generally, they have a very small amount of memory, like anywhere from like a pretty good sized microcontroller would have maybe 256 kilobytes of memory total. That's it, no more. A lot of the ones that are commonly used have even less than that. So Go, when you compile Hello World in Go for Linux, it's 1.3 megabytes. How are you going to fit that into 256 kilobytes? Well, you're not actually. Yeah. So TinyGo is really an amazing project founded by my colleague and collaborator Ike Van Latem. So they started this project about, I want to say, 6 years ago. And I've been trying to run Go on these tiny chips for years. At Intel, I tried to do it with some collaborators there. I went on Go Time, trying to get the community, but we tried lots of different things. But it wasn't until Ica really made that connection between we can use Go, but we do not use to only use Go. We can use this other thing as well called LLVM. So LLVM is a framework for building compilers that has been around for quite a few years now. It's actually the compiler framework used for a language called Swift that many people might have heard of. Another little language that's getting popular called Rust is written using LLVM. Zig is based on LLVM, even though they said they were going to try to stop using it, but then they changed their minds. Um, TinyGo is also an LLVM language. And this is how we're able to take, it's the same programming language, right? There is a formal specification for the Go programming language. And so TinyGo is the full programming language of Go. In fact, TinyGo is written in Go, just like the regular Go, Big Go, as we sometimes call it, right? But TinyGo then takes the single static analysis form, the SSA form. So when you write a compiler, generally speaking, the first thing you do is you look at the text and you parse it into, and you turn it into some type of representation of what the program means in terms of the operations that that language supports. You know, adding, subtracting, you know, whatever the things are that it can do. And reducing your human readable language to the form which you can then have your compiler turn into the binary part is known as SSA form. So since the Go compiler is all written in Go, and it's all part of the Go standard libraries, TinyGo takes those same packages and it creates this, it just is the normal Go compiler at that point to create this single static analysis form, this SSA form. But then we have the TinyGo compilers part still written in Go, but using an interface to LLVM, where we can then take and we can target the Go program to be compiled for these places where Go cannot normally even operate, like that Arduino I showed earlier, where it's a 8-bit microcontroller with only 32 kilobytes of RAM. Now, not all of your Go code will work in these small places, but a lot of it will. And so this is an amazing way to apply the same principles of, because Go is a very straightforward language. This is its strength, also sometimes its weakness, right? But it's, as far as languages go, it's very minimalist. It has a very small number of keywords. It's very straightforward how it works. The flow of control of the program is generally very straightforward. Now, sometimes the weakness of that is Go can be a little verbose to read. But the strength of it is that it can be it's verbose to read, so there's no mystery.
I'm not a compiler person, but the LLVM, that's like considered the back end of the compile, right? There's a front end and a back end. But is it because of that you have the WebAssembly support, or has the WebAssembly support been something different?
Well, first of all, what even is WebAssembly, right? So WebAssembly is assembly language written for a virtual processor, right? An imaginary processor, kind of imaginary. It was called WebAssembly because when they first created this assembly language, it was intended to be used in web browsers, essentially to achieve the goal of what Java was trying to do. As far as you could compile once and then run anywhere, right? But breaking it down to a bit lower language, a lower level, actually treating it like an assembly language where you have registers, and a stack, and operations. So LLVM was one of the first compilers to be able to produce this WebAssembly compiled code. And a lot of people started using it with something called Mscriptum, which is a C compiler, C and C++ compiler, that then uses LLVM to create this WebAssembly. Why would you do this? Well, there's a bunch of reasons. One of which is you want to write a bunch of code that's nearly native performant. but that you're not necessarily giving out all the code for. And it also will work on different operating systems and different browsers even. So all of the major browsers have had a WebAssembly runtime built in for quite a while. And in fact, Adobe, um, all of the Adobe Online, like if you use, Photoshop Online, it's all WebAssembly. It executes in the browser itself. So it's been quite well adopted.
I love the idea of thinking about it as a virtual processor, and that's the assembly that runs in that virtual. Actually, I love that idea. Now it like light bulbs go on when I think about it sort of that way.
But it's not just in browsers. That was step zero, if you will. Then a bunch of people said, what if we could run this other places, like in servers? Why would we want to do that? Well, there's a number of reasons. One of them is we might want to do things that require very high performance and low latency for starting up. For example, what if we want to create some plugins for our proxy server where we need to be able to keep up with the network traffic, doing some type of packet analysis or something. So uh, Envoy, which is a very popular proxy, the plugin architecture has been, and for quite some time, has been using WebAssembly on the server. So there's a thing called WebAssembly System Interface, or WASI, which is currently in what's called Preview 1, and it's being used by a whole bunch of companies in a bunch of different languages. Um, Rust is one of them. Go is another. Zig is another. C and C++, and some others as well. But really, in order to compile these things that will run at very high performant places like serverless web functions. So there's a company called there's a product called Spin from a company called Fermion, where there are a bunch of former Microsoft people who spun out with the support of the Bytecode Alliance, which is the consortium that's helping define and maintain the standards behind WebAssembly. So they have an amazing platform that's able to do insanely high performance for serverless web, basically serverless functions. Now, if you have done the serious work in the cloud side, you discover very quickly that it can become quite expensive. It's supposed to be cheaper, but it can become very expensive because it might take a while for your serverless functions. The idea is you have a function that does one thing and you put it into the internet so that you can call this function whenever you need it, but it's not running on a server that's running all the time. You're only basically paying for the computational processing when you're calling the function. Also when the function is starting and when it's ending. So the startup time and the cleanup time can be quite costly if you're using things like Google Cloud Functions or AWS Lambdas. And of course, they keep raising the price. Everything starts cheap and becomes expensive. The idea behind running, or one idea behind running WebAssembly in the serverless space is we're really talking about orders of magnitude less computation needed to do the same amount of work. The response time when you're using Spin with TinyGo compiled serverless functions is response time in the order of microseconds, not milliseconds, microseconds. It's really performant.
I always thought of, tell me if this is fair or I'm wrong. I always thought of WASI, WASI, as kind of like the system calls, like the same equivalent to like the operating system level system calls that basically gave you an interface to interact with everything below, but a standardized interface for your web applications.
That's exactly right. In fact, a lot of people will compare WASI to POSIX, which is, a standard for terminal-based applications, which, has allowed a lot of technology to keep operating for just years and years without any effort to keep it, doing so, just by setting a very low bar, certainly, for the capabilities. But by doing so, making it possible for a lot of people to get started. And also, one of the problems in technology is churn. You keep changing stuff. That's okay if you have a benefit, right? Like if my change brings me a benefit, I should make the change. But if I'm just changing things around for change, then I'm losing my energy, what they call opportunity cost. I could be doing something else. And it's creating unnecessary complexity. It's using up the time we have. So there has to be a good reason for change. But if we have a good reason for change, we should be changing, right? This is why technologies themselves are not the answer. They're part of the answer to a problem, but they're not an end to themselves. Even though they're really cool and I love them, don't get me wrong.
For kind of where I live in computing, I couldn't care less if my compiler produced a binary executable or some WebAssembly, right? Like it doesn't affect my life if my programming language gives me the feature functionality I want. What do I care what the final compiled and linked binary is, right? But I like the idea that I played with these web functions before even the cloud had them. Iron IO. I don't know if you remember about Iron
Oh
IO.
yeah,
Yeah, I was working with Iron IO. The cloud basically destroyed that company. But the biggest problem was how long it took, one, to queue it up, and then once it did, how long it took to actually get running, right? So the idea that I can get something running in microseconds starts to make that tech feel a little bit more usable. It's interesting.
definitely. But another aspect is you can use a different programming language to produce the same binary output. The standardization of WebAssembly means that you can write some code in Rust and compile it to WebAssembly. And you can write some other code in TinyGo and compile it to WebAssembly. And you can look at like what it produces and go, wow, it's the same exact code. In fact, we can even make it so we can call
You
our
don't even
TinyGo from
know.
Rust.
You don't
Right.
even
We
know.
don't need to care. Exactly. We don't actually need to care about that. And this is a very powerful idea, not because all programming languages are the same, but for the opposite reason, because each programming language can do some things really well, and trying to make it all homogeneous of like, okay, you can only use one language for now. It's like, nope, sorry, I'm gonna have to rebel against that whole principle. Like I cannot I love Go, it's a really awesome language, but it's not the last language I'm ever gonna use, I hope. I mean, if I'm struck by lightning later today, maybe, but no, it's really too late. I write programs. Just recently, I've been writing some Rust and some Zig as a part of a new project I've been working with in the WebAssembly space called Mechanoid.
Yeah, yeah, yeah. Talk a little bit about that project.
So we've been mentioning WebAssembly in the browser, and we talked about WebAssembly on servers. Well, if you know me, there's the final frontier is the device. Like when I say edge computing, I mean like the last centimeter. Like this is my edge computer right here, this badge. You know, the actual device. That's the edge, not a data center close to you. I mean, like hardware that is touching you, or you touching it, or it's touching your brake system, or you know, it's like the so WebAssembly can be run on the smallest of chips. It's not easy to do so, but it can be. And we can get a lot of these same benefits of having different languages producing the same binaries, and the encapsulation, and the small size of the binaries it produces. So Mechanoid is a new project that takes and brings WebAssembly to the microcontroller. So in Go, there's already a WebAssembly runtime written entirely in Go called WAS0. And we are now able to compile WAS0 so that it runs, in fact, it runs on this very badge that I was showing. Um, so we can compile WebAssembly in Rust or Zig or TinyGo and put it on that badge and run it. In fact, I can have my demo I was showing on this badge at the WASM IO conference recently that in Barcelona that I gave a talk. It's a little hard to see, but each one of these WASM programs This is the WASM badge. It actually runs Mechanoid, which is a framework for building WebAssembly applications on embedded devices. And so we're actually able to use this. Where's the buttons? There we go. I can choose which program I want to run. And then when I push the button, it'll run that WebAssembly program. So this is running TinyGo compiles Mechanoid to run on this badge. And then TinyGo also compiles the WebAssembly modules that run on it.
That's what I was going to ask you. When you deploy that program, it has everything in it. It has the WASM runtime and the WASI stuff, and then your program all compiled into one sort of distribution.
Well, that's one way to do it. And that's actually a really cool thing about in Go, we have the Go embed directive that lets us embed binary or textual data right into the single executable. So we can use that with Mechanoid and TinyGo, so we can embed the WASM right into the binary. But what if we want to do updates later, like over-the-air updates? This is actually a really serious problem in computing, but especially in industrial and device-oriented computing. If I put an update out to my device and it stops working now, what do? I can't update it again. It's bricked. Send it back. We'll send the tow truck to tow your car back to a service center so we can, connect it up to our special computer to reflash it. Sorry about the inconvenience, right? So being able to do over-there updates the binaries are smaller, so they're more viable to move them over wireless networking, for wide area networking, for example, mobile, cellular, LoRa, which is long distance radio. It's a more secure system because one thing about WebAssembly is it runs entirely in a sandbox. So you don't actually have direct access to the hardware, which is a great thing if what you want to do is create a platform. For example, if you want to create a smartwatch and you want to have it so different people can create plugins for this watch, or if you want to build a factory and you want it so that the people who are operating the factory can write small programs that control a particular process. It's not just a matter of set this setting to this and set that setting to that, but it's usually some type of logic, like, if this happens, then turn off that valve. And, so there's some actual logic, although it's not as simplistic as maybe some no-code programming or just settings, but it's something that can operate within a limited set of domains, right? So, there's video games. You want to create a video game platform that's, completely open, and you want it so anyone can create games and upload it to the portal. But you don't want it so that the device can get taken over, so it becomes, a spam sending device. So these are all some of the use cases where hardware and WebAssembly are a fantastic match. And Mechanoid it's the first, it's a completely open. There's been some other attempts to do like WebAssembly runtimes, but it's not just a runtime. It's using the WAS0 runtime. It can also use other runtimes, but it's trying to bring a batteries included framework approach of saying, here's how we think you should develop embedded and IoT applications, as far as the patterns are concerned. And you can then create the plugins or the add-ons or the logical modules in any one of these different languages, depending on what your particular needs are. So I think it's a very powerful idea, but it's pretty new. And so it's really, we just had the first release of Mechanoid about 2.5 weeks ago, about 3 weeks ago. And it's gotten a really exciting response. It was in InfoWorld, it was in GoLang Weekly. A bunch of people are trying to use it, ran into troubles, told us about what they were doing. We could fix them. No, there's all the beautiful, wonderful, amazing things about open source collaboration is, people will help you and you will help them. It's a mutually beneficial type of relationship. So it's pretty exciting. And some of the companies that have been, or organizations that have been trying to do this are largely been very closed. Like there have been some companies trying to do containerization of applications running on microcontrollers, but they generally haven't shown anything, just because they're not used to working in open source, which is, your first version you should be a little embarrassed about. Like it works, but only barely, or else you waited too long. You know, if it works for you, tell us. If it doesn't, also tell us.
All right, we got 12 minutes left here, so I want to use this last sort of 12 minutes for you to talk about the CV project that you're working on too much cool stuff, Ron. It's not fair, but talk about that stuff.
So GoCV is a Go wrapper around OpenCV. OpenCV is a framework for creating computer vision applications. I think it's at least 10 or 12 years old. Um, it's really the standard for doing any type of computer vision processing. It runs, pretty much on everything. Runs on Android, runs on Mac, runs on Windows, runs on Linux. Runs all these different places. It has an enormous collection of algorithms designed by literally several generations of doctoral and postdoc students working on computer vision research. Um, a lot of it, it's open source. There's also a separate collection of non-free algorithms, some of which are under patent if you needed to use them. Um, you have a whole deep neural network processing capability built in. It has the ability to use hardware acceleration with GPUs using something called CUDA. So OpenCV is really the standard for computer vision. And GoCV are the wrappers for Go around OpenCV. The project's been around for about 7 years. It has over 6,000 stars on GitHub, 150 plus contributors. It's being used in production many places in the world, factories like at Northvolt, where I've been consulting until recently. It's being used in retail establishments. It was part of an official set of reference platform applications released by Intel when I was working with them. And the reason why Go is so great to do computer vision with, I mean, well, most of the time these days when you see computer vision and machine learning, you see Python, right? And it's because Python creates a pretty great developer experience when you're working on trying to figure out how to get your algorithm to function. There's a thing called Jupyter Notebooks. Jupyter Notebooks are basically, it's a web page where you just enter in your Python code and you see the results right away. And you can combine these Jupyter Notebooks together with other machine learning functions. And it's a really great way to interactively try to figure out, how do I get this code working to do the thing I want? Because you can enter the code and see the result immediately. So this is one reason why a lot of the Python, centric. But then everybody goes, okay, great, this algorithm's working, let's go to deploy. And they're like, doesn't work on any other machines. Or it works great when we have one user, but somebody put it on, Hacker News and the thing crashed in like 5 minutes and actually the whole server melted down. So, Python is great for this sort of development experience, but it's not really geared up for production. In fact, there are things you have to try to do, whereas there is a language that's able to, out of the box, use all of the cores on a multi-core machine, where concurrency is actually built into the language itself. I wonder what language that could be. So, so there were a couple of wrappers around OpenCV, but the maintainers sort of fell off the wagon. They got tired around OpenCV 2 timeframe. We're on OpenCV 4. And I kept trying to convince people to work on it. Like I talked to someone, you see a pattern here forming with these open source projects? I try to get someone to work on it. I flinch first. Like, okay, fine, I'm just going to do a little code. Next thing you know, I mean,
Yeah, 7
well,
years
you know what
goes
they
by.
say? The first 50,000 lines of code are the hardest. Once you got the first 50,000 lines of code, then, it's all downhill. But, it's, we just came out with GoCV 0.36, most recent release, just in time for Embedded World in Nuremberg, Germany, which is where I'm going to be next week. We have really great CUDA support, works on all of the NVIDIA processors for doing hardware accelerated machine learning. Um, works on ARM, 32-bit, 64-bit, works on all the different Intel processors. Has many people who have added one feature to it. Actually, I would say the thing I'm really the most proud of what we've done with GoCV is there are a lot of people who've added one commit. It was missing the thing they needed, and they were able to figure out it was missing it and how to add that thing, and that thing got added. To me, that I'm getting actually goosebumps saying that, just because the most important thing for me with technology is making it possible for other people to use it. Getting rid of the professional programming priesthood that restricts access and making it possible for any human being to be able to put technology to work for them. That is my goal, my mission. My reason for caring about this is to help be a part of making technology available to improve the human condition. So when people I don't know and will never meet, probably, coming from China or India, or, next door to where I live in Spain, or any place, and they were able to use this to do something useful for them, that is improving the world, and that is a good thing to be doing. For me, that is a real testament to the power of open source to be life changing at the individual level, as well as the collective level. So, if there was one thought I would leave us with, it's, I still believe in the positive power of technology to improve human lives, but we have to think very carefully about how we apply it.
I love that. All right, and we are out of time, and I could talk to you for another 2 hours. Maybe I'll have you back for part two with Ron. All right, Ron, we're going to make sure to get all of this tech that we talked about in the show notes. But um, before we end here, if anybody wanted to reach out and talk to you after listening, what is the best way for them to do that? We'll put that in the show notes as well.
I'm on all the social medias as Dead Program. Uh, you can email me. If you go to GitHub, you'll find my email address is actually in my signature on all my commits, and I'm very brave. Um, if you ever wanted me to work with you on your project, you should reach out. I am a technologist for hire. I will write code for money for you. It could be closed. It could be open. It could be closed and open, or open and closed. This is what I do, and I really love it, and I'm always available to help other people do it too.
Yeah, and I recommend it if you have any projects and you're looking for someone with Ron's level of experience. He's a professional through and through, so he's the one to call for sure. All right, Ron, we are sort of done here. So thank you again for all the time that you've given us today. And I just want to say this is the Ardan Labs podcast signing off, and Ron and I hope to see everybody again real soon.